Welcome back to Rates of Reaction Lesson 5. This is on concentration and pressure, and if you're following the AQA scheme, there's a required practical that you'll need to do at school for this lesson also. So we are following the AQA specification. If you're from another exam board, then just make sure that everything we're covering in this lesson is what you need to know, and if you do need to find other bits of information, then you will need to get those from elsewhere. So students at the school where I teach, these are the resources we've got available for this lesson, and then also there are some page numbers there for the textbooks and revision guides that you might be using. As always, a little starter for the lesson. On the video version of this, you already know that the lesson is what the lesson's on, but if you've forgotten, then you can have a quick look at this picture and it might help jog your memory. See if you can link each of those pictures to the lesson title. So top left there, you've got different concentrations of a solution. Then there's a pressure washer. Then we've got two diagrams where we've got particles inside the same size box. So there's a greater concentration in the lower box there, and there'd also be a greater pressure in the lower box. Okay. There's a pressure cuff doctors use to measure blood pressure. They're slightly more modernized now, but that is a pressure cuff nonetheless. Then a physics diagram there, so pressure equals force over area. And then bottom left, the concentration camp, so slightly different use of the word concentration, but it does, several of the science words and terms that you come across do have different meanings elsewhere. The middle diagram at the bottom, a gentleman concentrating, or he could look like he's under pressure. And then on the right hand side there, Freddie Mercury, the lead singer of a band called Queen, sang a song about pressure. Alright, pause the video if you want to look at what the specification says about this lesson. Just draw your attention to the bottom there, the required practical activity. Okay, where you have to investigate how changes in concentration affect the rate of reaction. Lesson objectives and outcomes. Again, pause the video if you want to look at these in more detail. Right, so what do we know already? This question we've had several times now. Do all particle collisions lead to a reaction? You should know the answer is no at this point. So not all particle collisions lead to reactions. They need to have sufficient energy, what we call the activation energy. Remember, that's the minimum amount of energy that particles need in order to react. And also, particles need to collide in the correct orientation. So if that's happening, then we're getting a reaction. So we then looked at rate of reaction, and there are two things that determine the rate of reaction. So it's how frequently the particles collide, and then also the energy with which the particles collide. So previously we've looked at surface area, where we changed how frequently particles were colliding. We then looked at temperature, where we changed how frequently the particles were colliding again, but also we by increasing the temperature, we gave a greater proportion of the particles the activation energy. So we influenced both factors on that one. So today, again, we've got to keep those in mind, keep those ideas about the frequency of collisions and the energy with which particles collide when we're looking at concentration and pressure. All right, we've got a little example here where we've got a classroom. Okay, we have to think of this as a 3D classroom. Okay, it's just a 2D shape there, but imagine it's a classroom with these people in, and we want to try and make these people bump into each other more frequently. And there's two ways that we could make people in a room bump into each other more frequently. All right, just think about how we could do that. You need to maybe think a bit more abstractly as well. We could change a few things. So think about how we could make it so that these people would bump into each other more frequently. Good. All right, one option is we could put more people in the room. The room has stayed the same size. Okay, we've got more people in there, so there's going to be more frequent collisions because each person has less room, so they'll collide more frequently. Okay, keeping that in mind, that's that kind of principle we've put in place there. Can you think of what the other option might be? Good. Make the room smaller. Right, we keep the number of particles, the number of people the same, but the space that they're in we've made smaller. All right, so the lesson is about two factors that are affecting rate of reaction. Can you link those two factors that this lesson's about to those two ideas that we've got? Okay, so we've got the one on the left where we're increasing the number of people in the room. Okay, that's going to be one of the things. And then we've got the option on the right where we're keeping the number of particles the same, but we're just making the space that they're in, we're making that room smaller. Okay, so what are those two things? What are the scientific terms for that? Excellent. Concentration and pressure. So increasing the number of particles or the number of people in the room is changing the concentration. And increasing the pressure is by making that room smaller. And in both of these, what we've done, what we've actually influenced, we've influenced the number of particles per unit volume. All right, so in both those examples, in both the concentration and the pressure, we've increased the number of particles per unit volume. All right, so we're going to look at that in a bit more detail now. So by increasing the concentration or pressure, you can calculate what has happened to the density of particles or people. Right. So if we remember, these are our 3D rooms. Okay, so we've got some measurements there. So these are effectively cubes. So if we were going to measure the volume, okay, of this room, the room in the middle there, it would be 8 times 8 times 8. And then the room on the right there, the smaller one, would be 5 times 5 times 5. And this is to try and demonstrate to you how we're basically changing the amount of room that particles have. So the more room they have, the less frequently they'll collide. The less room they have, the more frequently they'll collide, and the faster the rate of reaction, because we know that rate of reaction is linked to the frequency of collisions. All right, a quick calculation there. So the volume of the big room is 512 meters cubed. So that's the same for the diagram on the left and the diagram in the middle. The volume of the room on the right, okay, 5 times 5 times 5, is only 125 meters cubed. So the volume is smaller there. If we stick with the middle one, the one we started with, we've got 10 people in there. Okay, so we've got 10 people per 512 meters cubed. So each person effectively has the density in there is 0.02 people or particles per meter cubed. Now then, if we go to the left where we've increased the concentration, we've put more particles or more people in there. So this time our density, if you like, is 24 divided by 512. And each person has 0.04. There's 0.04 particles per meter cubed. So the number of particles per meter cubed, all right, has doubled. We've doubled the number of particles per meter cubed. So there's many more particles in there. They haven't got as much room, and so they're going to be colliding more frequently. On the right hand side, what we've done there, we've actually made the room smaller. Okay, we've kept the number of particles the same, and so it's 10 particles divided by 125. So the density of particles in this room is 0.08 particles per meter cubed. So there's almost 0.1 particles per meter cubed. So the space between particles in the pressure example there is a lot less. So there's going to be more frequent collisions there, and the rate of reaction will be higher. Right, so just note how the number of particles per unit volume has increased, and this is what leads to the more frequent collisions. So when you talk about concentration and pressure in exam questions, you must reference the number of particles per unit volume. So if you're increasing the concentration, you'll be increasing the number of particles per unit volume. If you're decreasing the concentration, you'll be decreasing the number of particles per unit volume. Likewise with pressure, if you increase the pressure, you're increasing the number of particles per unit volume. Okay, that's a key term that you need to write in order to get marks. And then the second point that you need to say is that is linking that to the frequency of collisions. So we're going to use our collision theory now to explain the effect of concentration and pressure. So we've got some diagrams here. There's one with a graph that's the reaction between marble chips and hydrochloric acid, and we've got different concentrations of hydrochloric acid. So what we've done with this reaction, we've got the marble chips in a conical flask, and we've got it on a mass balance. And if you remember back to our measuring rates lesson 1, okay, this is one of the methods we can use. So if a gas is being produced, the gas is going to leave through the cotton wool in the top of the conical flask there, and the mass of our reactant vessel will gradually go down as more gas leaves. And the graph is showing you how that changes with different concentrations of acid. So the line on the left, the highest concentration, the mass decreases quite quickly and then levels out. And then the lowest concentration one, it decreases at a slower rate. Okay, it's not as steep, so a slower rate, and then levels out again at the same point. And then you've got the two diagrams at the bottom to show how we've got the same space, but we've increased the concentration in the diagram on the right. And so you've got to link that to the frequency of collisions. So use what you know about collision theory and altering the concentration to explain the results graph. Have a go at doing that now. Right, hopefully you've come up with some plausible explanations. So for the low concentration, this would be the same kind of answer that you'd write for low pressure as well. Okay, so for low concentration, this is our blue line, there's less particles per unit volume. So there's less frequent collisions, so the rate of reaction is lower. So the reaction loses mass more slowly. Right, so we're linking it to the number of particles per unit volume and also the frequency of collisions. For the higher concentration or higher pressure, okay, so this is our green line, there are more particles per unit volume, so there's more frequent collisions, therefore the rate of reaction is higher and the reaction loses mass more quickly. Okay, so again, we're linking the number of particles per unit volume and the frequency of collisions. Like we've seen before, both of these, like all three of these lines, there's three lines there, all three, they level off at the same point. Okay, that's because once the reaction's over, okay, it can't continue, and so it will finish at the same point. All right, at school, what you would be doing, you'd be doing a required practical for this by changing the concentration of one of your reactants and looking at how that ultimately changes the rate of reaction by measuring either the time it takes for a precipitate to make it go so cloudy that you can't see across, or you might be measuring the rate at which some gas is produced, either with a gas syringe or an upturned measuring cylinder. But it's important to know that when you get asked questions about this in exams, all right, they could ask you a whole range of things. They're not going to ask you always exactly what you did. They might change some of the reactants. I mean, we would use sodium thiosulfate and hydrochloric acid. They might use a different set of reactants in an exam question. But the sort of things that they might ask you about is calculating an average from some results. Remember, you need to exclude any anomalies before you do that. So an anomaly is a data point that doesn't fit the trend. So you'd exclude that before you did your average. Identifying suitable apparatus for the task. So in the first video, we looked at what some of that apparatus was called. Okay, and you need to be aware of the actual scientific names for things. Okay, you can't just say a pot, a glass pot. You'd say a beaker. Identify suitable apparatus for the task. That's what we just said. Identifying independent, dependent, and control variables. So remember, independent variable, that's the one that you change. So that is the thing that you change. So in this example, you would be changing the concentration. The dependent variable is what you measure. Right, so again, for this one, the dependent variable will either be the time taken for the cross to disappear, or it could be the time taken for a certain volume of gas to be produced. And control variables, these are what you keep the same. So in this example, you'd have the temperature the same. You would keep the concentration of your other reactant the same. The apparatus you use, you'd keep the same. So these are all things that you want to make sure are having no influence on your results. You may be asked about health and safety. Okay. Again, with these questions, it must be relevant to the experiment that you're doing. You can't just put a random kind of wear goggles. Okay, you must think of something that is going to be specific to this particular practical. And then quite frequently, there's a longer question describing how to carry out the investigation. All right, don't just regurgitate what you've done at school. You need to check that check in the question what reactants they're using and what it is they want to measure. Okay, the clues are all there in the question. It's just quite frequently students are so desperate to get down some information that they just put down exactly what they did when they did it at school. Okay, you must read the question. Okay, that brings us to the end of today's lesson. Coming up, we've got a final thing to look at in terms of affecting rates of reaction, and that's catalysts. So that will be the next lesson, and I hope to see you next time.